Hi, this is a supplemental video on linking electron configurations and valence electron configurations to the periodic table. So first things first, we can correlate the number of rows with the principal quantum level, or n. So the first row is n equals 1, 2, 3, 4, 5, 6, 7. So currently, our ground state electron configurations go up to level 7, can go up to level 7 because at this point in time, we have 7 levels or rows to the periodic table. So how does this line up with electron configuration? Let's start with the electron configuration for lithium. So if we locate lithium on the periodic table, so here's lithium, there we go. Lithium has 3 protons, which means a neutral lithium atom would have 3 electrons to balance out the charge to make a neutral atom. So let's use our rules to fill the electron configuration for lithium. So if we elect for electrons, we're going to start with our lowest n level, which is 1. We'll pair those electrons. We have one more electron. Our n level 1 is completely filled, so we're going to bump up to n level 2. Now n level 2, we can either start with 2s or 2p. 2s is lower in energy, so we will put 1 electron in 2s. So for lithium, we have an electron configuration of 1s2, because we have 2 electrons in the 1s orbital, and 2s1, because we have 1 electron in the s, and the 2s1. If we were to go next over on the periodic table to beryllium, so beryllium, there we go. Oh, whoops, that wasn't meant to scribble over beryllium, that's fine. So we have beryllium. Beryllium has 4 electrons. So our first 3 electrons are going to look exactly like lithium, but now we have an extra electron that we have to place. So we have 2 options. We could either put the 4th electron in the 2s and pair it, and that would come at an energetic cost because you would have to put 2 electrons together that want to repulse each other, or we could pay an energetic penalty by putting that electron in the next higher up energy level orbital, which would be, or a sublevel, which would be a 2p. In this case, there would be less of an energetic cost to pair the electron in the 2s orbital, so we are going to pair that electron in 2s. And so, if we were to look at the electron configuration for beryllium, we would get 1s2, 2s2. All right. So, what we see here is that in lithium, if we were to look at our valence electrons here, where our valence electrons are the electrons that are in the outermost n level, lithium has valence electrons of 2s1, whereas beryllium has a valence electron of 2s2. And so, and if we were to go and look at, say, sodium, if we were to go through and align and figure out where sodium ended, we would find that sodium would end on 3s1, whereas potassium would end on 3s2. And so, we refer to groups 1 and 2 as our s block elements because the last orbital filled in the valence shell is the s block. And so specifically, our elements in row 1 are going to have an electron configuration of ns1, and in group 2 will be ns2. Now, we can go the opposite direction. So let's say, for instance, I was to give a valence electron configuration of 7s2. The way you could back calculate to figure out which element that would be to say, okay, first things first, I am going to end on n level 7 if I am 7s2. So if I go to 7, francium would be 7s1 because it would have one electron in its valence shell. So the answer for this would be radium for 7s2 because it would be, its outermost level would be n level 7, and it would have 2 electrons, both of which would go into the s orbital. So now let's progress over to the p block. Right, so this is going to be over to the groups 13 to 18. So let's look at the element boron. I'm going to erase sodium and potassium down here. There we go. So if we look at boron, boron has 5 protons, which means that boron would need 5 electrons to balance out and make a neutral atom. So if we were to place another electron in boron, we would put it in the 2p orbital. And so if we were, so we would have 1 electron hanging out in the 2p orbital. So we would represent the valence electron configuration for boron as 1s2, 2s2, 2p1. All right, so that's boron. Now, if we were to look at the valence electron configurations of boron, we want the orbitals that are going to be in the outermost n level. And so in this case, we would have 2s2, 2p1. Let's go and let's take a jump and let's go over to fluorine instead. So fluorine has 9 electrons, so we are going to want to add in another 4 into our p orbital. So when we are looking at a sublevel, the orbitals within a sublevel are degenerate, which means they have the same energy level. So we would want to individually fill each orbital, so we maximize the distance between the electrons, which means we minimize the electron repulsion before we go back and pair. And as a result, we are going to have 4 electrons in our p orbital. So if we were to write the electron configuration for fluorine, it would be 1s2, 2s2, 2p5, with our valence electron configuration being our outermost n level, which is 2s2, 2p5. Now, let's take a minute and see how this electron configuration maps onto the periodic table. So both boron and fluorine have their 1s filled. They also have their 2s filled. However, and both of those s's, the 2 s's, are going to count towards the atom trying to achieve a full octet when it forms a bond with another atom or polyatomic ion. However, if we look at boron, boron has NS2 and P1. Boron ends on P1, whereas fluorine ends on P5. And so what we can do is we can use the position in the periodic table to predict the electron configurations of elements in here. So we know that boron has the part of the valence electron configuration of beryllium, and that it has this 2s2 filled. 2s filled with 2 electrons. However, when we bump over to this part of the periodic table, we are one element in, whereas on fluorine, we are 5 elements in. And that happens to line up with the number of electrons that are filled in the p orbital. So we can refer to this part of the periodic table as the p block, because the last orbital filled in the valence electron configuration is the p block, and then the number of spaces into the p block you are is the number of electrons that are contained in the p orbital. Now, When we start getting into N level 4 and we get to our metals that are contained in the periodic table, things get a little bit funky. So let's take a look at titanium. Titanium has a number of 22 protons or 22 electrons. So let's go ahead and fill in our electron configuration. So we are going to fill that p orbital. We'll go into 3s, so corresponding to here. Next, we'll go and we'll fill 3p, because we have 6 electrons. 1, 2, 3, 4, 5, 6. The next orbital to be filled will be 4s, so that's the next one down and to the left on the periodic table, but also the orbital that's next in terms of the next highest energy in terms of our energy diagram. We'll go and we'll fill in those 2. And once we account for the math, we've used up 20 electrons and we have 2 left over. So we have to make a decision if we're going to put those remaining 2 electrons in the 4p orbital or the 3d orbital. And there's 2 ways that we can figure out what comes next. The first is we look at our energy diagram. So 3d is lower in energy than 4p, so 3d is going to be filled first. Our other option is if we look at the periodic table, now this block here, that row of elements from 21 to 30, so scandium to zinc, corresponds to the 3d orbital being filled. So the 3d row of elements, where the electron configuration ends on 3d, is adjacent to 4s, so we will fill it next. So instead of in row 3, where we went from 3s and we hopped over to 3p, now in row 4, we have to go through 3d before we can fill 4p. We have to go through 3d before we can get to 4p. And so we are going to put those 2 electrons into the 3d orbital. So if we were to write out the full configuration for titanium, we would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, zoom out a little bit here, 3d2. So now the question becomes, what is the valence electron configuration for titanium? So I'm going to use an example of what one of the cations titanium becomes to demonstrate this to you. So in nature, one of the occurring forms of a titanium cation is titanium 4+. And so we can rationalize where titanium would take out its electrons to achieve a 4+ state to rationalize which are the valence electrons. So, for titanium to pull away electrons, it's going to start by pulling away electrons that are the furthest and the highest energy from the center of the atom. So, if we look, the orbital that is the highest in energy is the 3d. So in theory, in terms of energy, the 3d electrons are going to be the easiest to pull off. However, the 4s electrons are physically further away from the center of the atom. And so, titanium assumes a 4+ charge because it can pull 2 electrons from the 4s and then 2 electrons from the 3d. And so we can rationalize that for transition metals, which are located in the D block, have an electron configuration of ns2, n-1p, or n-1d, not p. We'll erase the p, sorry. We'll put the d there. Because those atoms are going to pull from the S because it's the furthest away, but then when they run out of S electrons, they are going to pull from the D orbital because it's in the new outermost n level. And of all the sublevels in the 3s n level, 3D is going to be the highest in energy and therefore the easiest to pull away.